It's a popular meme in these crime dramas like CSI, where you're analyzing data to try to catch a criminal, that they have the ability to instantly and infinitely zoom in on an image. Now, the good ones don't do that, but some bad ones who really aren't based in science will take a grainy black and white photo from someone taken across the street on a very cheap camcorder and somehow magically zoom in and create this color image of detail of the killer's face. And in one actual CSI episode, they actually caught a reflection off a killer's eyeball, which is ridiculous. Because lenses like your eyeball or camera lenses in any camera, they have edges. And because they have edges, there's diffraction around those edges. That diffraction affects the ability to resolve small details. So there's a limit to what you can do as far as zooming in with a lens. You cannot snap a photo and then just keep on zooming in Photoshop and see more and more detail. It doesn't work that way. And of course, it's limited by pixels in your digital camera, but even if you had an infinite number of pixels in your camera where you could keep on zooming and zooming and zooming and not see the individual pixels, you would not be able to see any more detail because the image itself would be fuzzy at small angles. So the Rayleigh criterion is actually a measurement of the limit of resolution of an optical instrument. How small a detail can it see? And it talks about a resolvability angle. So theta sub r here, your book doesn't use the sub r, but I do just to associate with its Rayleigh criterion. Theta sub r, this is the smallest angle you can resolve using an optical instrument, is equal to 1.22 times the wavelength of light that you're seeing over the diameter of the lens. So for people, diameter of a pupil is about 7 millimeters when it's relaxed. Plug in 7 millimeters here, the wavelength of light we're looking at, 550 nanometers, is a pretty typical wavelength. That means it goes from 400 to 750. Plug those wavelengths in, and that will tell you what the resolvability is of the human eye. What's the smallest angle we can see using our eyeball? Now that becomes important when we're looking at computer monitors or smartphones, right? Smartphones and computer monitors have pixels in them. Those pixels, if we can make them close enough together that we cannot see the individual pixels, if we make them closer together than our ability to resolve the angle, then we actually see, when we look at a television, when we look at our smartphone, a smooth image. Now there's a branch of art that does this called pointillism, where the art itself, if you get very close, is just made up of tiny, tiny, tiny points of paint, just different colored points of paint. But when you stand back, you see, your eye can't resolve those individual points of paint, so you see the full image. Now, early smartphones didn't have this technology. The pixel density wasn't high enough, and we could resolve the individual pixels. Or old TV monitors, old computer monitors. Especially if you get close to them, you can easily see the individual pixels. So in order to see a smooth image, the pixels have to be closer together than our ability to resolve them. Now this doesn't tell you the physical spacing of the pixels, this just tells you the angle that we can resolve something. So if you want to get the distance, for example, if this is our ability to resolve, this tells you the distance when the object is some distance d away. So for a smartphone, it might be, when we read our smartphone, it might be 1.5 feet or 2 feet from our face. Using the angle calculated here, we can calculate how close those pixels need to be. And they need to be like microns apart. And they are today. So this equation here gives you that relationship between the resolvability of a lens system. Now, the way you can actually improve your ability to resolve something, you can do two ways. One, you can change the wavelength. The smaller the wavelength of light, the better you can resolve it. So blue light does a better job of, you can more easily resolve details in blue light compared to red light, almost a factor of 2, because red light has almost a factor of 2 higher wavelength than blue light. Or you can increase the diameter of the lens. And that's one of the reasons that astronomers make these really, really, really big telescopes, because then we can resolve smaller details in distant objects. When we take a picture of a very dense cloud of stars, chances are some of those stars will be very close together. We want to be able to resolve those stars, right? We want to be able to see, is that one bright blob there? Is that two stars very close together, or just the light from a single star? We don't want to get it wrong, because we would come to incorrect conclusions if we got it wrong. So we build large telescopes in part to help try to resolve these distant star fields. Now, that's for astronomy. For biology, which most of you in the health sciences are probably more familiar with, you can look at for microscopes. So you can use the Rayleigh criterion and apply it to microscopes, and your book goes through this derivation. But here, X represents the separation between objects. Like, for instance, how far apart are cells? If you're looking at a blood smear and you have white blood cells, you want to be able to resolve the cell boundaries. Well, a cell is, think of it as a little bubble, right? A little bubble of material, a little spherical object. Well, what's the separation between the edges of the cell, or one cell to the adjacent cell? That's X. 1.22 comes from the equation above. The wavelength is still there. The lens diameter, this is the diameter of your objective lens in your microscope. D here, small d, is the distance from the specimen to the objective lens. That's, again, you have a slide and you have your objective lens sitting above it. D is that separation. How close is the specimen to your objective lens? If you know how close your specimen is to the objective lens, if you know the diameter of the objective lens, if you know the wavelength of light you're using, you can determine how close together objects can be minimum in order to resolve them. So if they're smaller than that distance, you wouldn't be able to tell there are two objects there. If they're bigger than that distance, you would. Rewriting this in terms of that numerical aperture, which we talked about when we talked about microscopes, and the index of refraction, which again was important when calculating the amount of light gathered in to a telescope through numerical aperture. The separation between objects, or the minimum resolvable separation between objects, is equal to half this value, 0.61, times the wavelength times the index of refraction over this numerical aperture. So this gives you the minimum separation of objects in a microscope. This general form gives you the resolvability angle depending on the diameter of the lens you're using, microscope, telescope, your eyeball, whatever lens you're using, and the wavelength of light. So incredibly useful in determining your ability to resolve small objects. And this assumes, of course, perfect vision for humans. Even if you have a lens diameter of 6 or 7 millimeters, your pupil, it doesn't mean you can resolve things this close. That just means that this is the physical limit of what you can do. Right? Superman, with perfect vision, would not be able to beat this. This is he can beat most laws of physics, so maybe he can beat this as well. But you cannot do better than this. There's no magic way you can create a small lens camera that can capture detail at very small angles. It's not physically possible.